Hey Isaac, welcome back everyone.
Hey, Aaron. I think when we left off, we had just kind of decided to change our strategy a bit on the segmented array insert and remove implementation. Do you want to give an overview of the new strategy, Aaron?
Yeah, good. So we were thinking maybe we take the same idea of, so if we step outside of the segmented array, the way we use it is we've got two segmented arrays for keys and tables. After a compaction, we're going to remove some tables, insert some tables, and then after that, we're going to, yeah, those two, and then after we've done a whole lot of modifications there, we're actually going to throw away our root index and just rebuild the root index from scratch. So it's kind of like a brute force approach, and it's much simpler. Maybe it's a little bit quicker because it's less branchy, but most of all, it's just much safer. And so then the idea was maybe, oh, also, yeah, if we just rebuild our root here, it's much easier because we also don't have to mess too much and integrate with the segmented array, what's happening inside there. So we can keep stuff just nice and separate, easier to think about. So now what we're wondering is if we should take the same strategy for segmented arrays as well, where you can mutate the array, do lots of inserts and removes, but while you're doing those operations, it's not trying to garbage collect all the time. Rather, we do all the bulk inserts and removes. And then after that, we have a separate segmented array.compact method, which then like super compacts the segmented array. And the idea there is we're making a trade-off. So we're making the insert or the update path for inserts and removes, we're making that slower, but that's because we're aware that that doesn't happen all the time. And even making it slower is still not going to really be noticeable. And in exchange for that trade-off, we then optimize the lookup path. Everything that is, working off the segmented array in the hot loop then becomes faster because we're keeping our data, instead of only using 50% of the node, we're now starting to approach 100%. So if you do the cache miss into a node, you've then got the prefetcher is working with you and maybe better performance in the comment, like the 90% case is now then getting faster. And in a way, it seems kind of simple, like to reason about, because just go and change a lot of stuff and then call compact once. And then, yeah. But I'm kind of glad we've had a nice hour and a half break, Isaac. I don't know what you think.
Yeah.
Have you had any new thoughts since, like on this? Can you see
Um,
how it could work or see any showstoppers?
I think I definitely have I'm pretty comfortable implementing that. I think it seems pretty straightforward to implement,
Yeah,
and it's pretty nice too. I think there's not for our use case, it fits well, and that's why we're doing this there
yeah,
as well. It's just like we just want to fit this data structure to our use case perfectly, and so I think
yeah,
it makes sense to do it that way.
yeah,
Um, and so we still do need to split nodes during insertion because if a node is full, we still need to put the new data somewhere before we can then rebalance things.
yeah,
So we'll still have that, um, but during removal, we can just leave empty slots in the node and make the node as empty as we need it to be, and then only discard nodes during compaction of the segmented array.
yeah,
Um, did
yeah.
you
Good.
think of any showstoppers or anything?
Yeah,
Um,
I'm happy that you can see like how to do it like that, and it helps me also. Then it's then I also see it. I think I like it because it's nice and intuitive. Um,
yeah,
and but the one thing where I think we might run into trouble is if we doing so we've worked out the memory allocation of all the nodes. It's all statically allocated. So
right.
we've just got to be careful then, because if we're removing tables and we're not doing the incremental GC, then we're removing tables, which means the whole node is free. Then we try and insert tables later in a different place. Now our static allocation requirements might be exceeded. Uh,
Okay. Yeah, I see what you mean. Um, it depends on like how many inserts and removals we do. Like what's the cap on the inserts and removals per compaction?
Yeah.
Because if there's an upper limit on that, we can just like allocate enough nodes to fit the difference there. Um,
Exactly.
you see what I
Yeah.
mean? I
Yeah.
think there
Yeah.
probably is though, too, because we have a maximum number of tables we were expected to get out of the compaction algorithm.
Yeah.
So I think we can manage that. We have to be careful, you're right, but I think that's not a showstopper really.
Yeah.
Um,
And one way to improve the API so the user doesn't get that wrong is we could always make it that it's like bulk remove, and at the end of the bulk remove, it calls compact internally. So we just do two
okay.
compacts. We do remove compact, insert compact, but the user doesn't have
That
to
would be
worry.
make it foolproof though, but then we like waste a whole compact, so we
Yeah,
can make it faster then too. Or
yeah,
maybe that's what we should do first. Just make it um, yeah, trivially safe.
yeah,
Um,
yeah, yeah,
make
exactly.
sure there's
Yeah,
no way things can go wrong.
yeah. Because it does seem like even that does help the bulk case because we're not doing incremental
Yeah.
compactions. We just do it once
Or we can
across
just
all the
not
node.
compact on insertions. That's the other thing we can do. We can only compact on removals. Insertions we already have implemented without compaction.
Yeah.
Um, I guess
Okay,
that
yeah.
would just make bulk insertion potentially slower, but we could also just come back to really evaluate that in the future.
Yeah.
Um, so right now we've got insert. It kind of already even has it has a split nodes even if you are doing compaction. I think they could maybe get. Yeah, I'm not sure if that even gets faster if you know you're doing compaction. If you can make insert much better. So I
Yeah.
think we just don't do compaction after insertion, only after deletion, and so
Okay.
should
The
work out,
one,
right?
yeah, yeah, I think that's a great idea. The one advantage if we do compaction after insertion is that we're then going to get make all our nodes 100% full. But
Right.
but I think what we
But
would do then is we wouldn't make it 100% full. We would amortize it so that we make the nodes 90% full. So that
yeah,
way we amortizing the compaction because otherwise if we do 100% full, the compaction after insertion is literally going to do a full men copy all the way to compress
oh
down.
yeah, yeah, that makes sense.
Yeah, but
Yeah,
I
cool.
so are you happy that we do a compaction after insertion, but just have a high load factor?
Um, sorry, can you repeat that? I was thinking we wouldn't do it after insertion, but we would use a high load factor or have the compaction after deletion use a high load factor so that then
Okay, yeah,
subsequent inserts just would not have to split nodes every time and
yeah,
still don't do it after insertion.
yeah,
I'm not sure why we'd have to do it after insertion, to be honest.
yeah. Because I guess like after compaction, we're inserting one group of tables into the array, and that's it.
Yeah.
We're not going to do multiple inserts. It's just going to be remove one group of tables, insert another group of tables. So it's only the zone where we insert some tables where our segmented array won't be um, high utilization. Uh,
Yeah. So maybe you want to do the inserts before the removals then, though. Um, 'Cause if we do insert, then, well, maybe not. 'Cause you still, the cycle is going to be still the same. You're always going to have to do inserts after compaction, and so just doing
yeah,
90% full um, when we compact, I think it makes sense. Then we leave space to insert into, and we can tune that 90% number too, like based on
yeah,
real world usage and what we
exactly.
see.
Yeah, yeah.
Um,
Yeah, because it's only the segmented array will then only be not highly loaded in the two nodes or more where we've done some inserts. If we did do the inserts before the removes, I think that's a good idea. The only problem is that we then break our static allocation limit.
Yeah, exactly.
Yeah.
And also, it doesn't really solve the problem of having the 90% load because then on the next compaction, you're gonna have to do inserts again, and then
Mm.
semantically still right after you've done the removal. It's like
Yeah.
I think things will be compacted as if you did the other way around.
Yeah.
So I think doing removes first, then running compaction at 90% load roughly, and then doing inserts is the way to go. And then the inserts, they're gonna be contiguous. So I think the worst case is they like have there's like then two nodes that are half full instead of all the way full.
Yeah.
or something like that. And so that's also like not bad.
Yeah.
Um,
And what we can even do is while we're on it, because we've got this all hot in our cache, like we understand it
yeah,
all, it might be worth it just to do the bulk insert path where we actually calculate how many nodes do we need to insert and just do it as one, um, so that we're not,
yeah.
because that way we're
I
also
think
then keeping it fairly compact.
yeah, I'm not totally clear what the API is there. It almost feels like we wanted like the most optimal thing would just to be or um, have an API that does both insertions and removals and just takes a slice of things to insert and a slice of things to remove and figures it out internally,
Hey, there we go.
and then compacts afterwards.
That's what we should do.
Um,
Yeah,
and that'd be
that
the only
makes
thing we
sense.
expose for compaction.
Yeah,
And then we have kind of the freedom to optimize that as we choose. Um,
yeah, yeah, that makes sense. The
Probably
only
by
thing that,
first doing,
yeah,
yeah, go ahead.
yeah, I was also wondering over lunch, like, how do we must just be careful with indexes. If we remove tables, then the indexes of the inserts change maybe, or, um,
Oh yeah, that would be tricky.
so if we're doing, I really like the idea of a single method that does removes and inserts. It's basically like a splice method. Uh, in JavaScript, you can splice an array, removing stuff, adding stuff, and
Yep.
it does it all in one. Actually, that is one of the cool things in JavaScript. Like, despite all the waste in other parts, that's kind of what we're thinking.
Yeah,
So,
I think, yeah, I'm kind of feeling like this is, we want to have a more clear idea, or like a very clear idea of how we're going to use this API though before we write it. I'm
hmm,
not sure. Like I'm not totally crystal clear in my mind on how or how these things will be called by the compaction iterator,
yeah,
um, in the LSM tree. And
it's
like if
gonna.
there's really a fixed, if it were like, do the number of inserted tables always match the number of deleted tables? I don't think so, no. Isn't it like
Uh,
deleting from one level and inserting when to a different level too?
yeah, I can run it through it for us if you like.
Sure.
So when we compact, we will pick one table in a level. Um, then we will pick all the tables in the level below that overlap that one's key range. And there is
Okay.
some fixed upper bound on that, um, because our previous compactions would have ensured that that upper bound is not broken. So it will be like for one table here times the growth factor, that many tables in the next level. And then, so those are the tables that are inputs to the compaction, and they're across two levels. Then at the end of the compaction, those are the tables that will get deleted. And then that compaction of the 11 inputs, if there is very high fragmentation, we might only output one table or two or three. But in the worst case, we're going to read in 11 and we're going to output 11. We can't output more than what we read in. We can't, um, yeah, we can't, that would be injecting
Cool.
new data. So it's basically read in 11, write out 11. And that's it. So at the end, and we're going to do that atomically at the end of the compaction. Once everything is done, we will switch it out in one go, removes,
Yep.
inserts. Uh, so I don't know if you're happy that we push on and actually do our bulk API, and maybe we get it done in the same time, and then we write the tests for that, and we're done, and we don't have to come back to it ever. Like,
Yeah, I feel like we're gonna end up coming back to it at some point. Um, um, I'm cool about writing a bulk API for remove, because that we don't already have one for there. But I
yeah,
think writing the bulk API for insert, it gets a lot trickier.
yeah,
So I'm not even sure like what you can do here to make it better in bulk. Um, I guess just split the node earlier. If it's only like 10 tables, though, it won't really make much of a difference.
Yeah, yeah. I think it could be not as difficult. Like we think of it as insert elements, takes in a slice of elements to insert, and it takes the current node that we're at. Has it got any free space? If it has, consume from the slice and shorten the slice until we fill up that node. Then if there's still more elements, we can, at that point, we can then just insert an empty node and fill it up.
Okay. Yeah,
Or,
so not even worry about splitting it. Then we also require rebalance after insert, you're saying.
yeah, we could do then a rebalance after insert, but actually, or what we could do instead of inserting an empty node is just go onto the next node and say, does that have space, and shift those elements and put in what we can. But maybe it's just easier to just insert a node, put stuff in, but then the node is going to be less than half full.
Right.
But I kind of don't mind just to rebalance after the insert and just squish everything all the way down.
Yeah. Ideally, we only have one rebalance for the insert and the deletion.
Yeah,
Um,
yeah,
I think that just requires a tiny bit extra, it's like one extra node or something, to make sure
yeah.
that we don't go over our static allocation then.
And then we can just guarantee with comp time assertions that our static allocation does handle that case.
Yeah. I think that works, yeah. Shall we try that then? Or you
Yeah.
want to do deletion first?
As you, whatever you're excited. Are you also on board? Like you think it's worth that we do it?
Sure, yeah. I think it's not that hard if we do the rebalance thing. Or maybe we should write rebalance first. Um,
Okay, good.
I
Yeah,
think that sounds good to me.
yeah.
I'll just take it like down here under remove. Is rebalance the right name for this? Like, I think it's more like compact.
Compact, yeah.
And this just takes a self pointer. I don't think it needs anything. Oh, it needs the node pool.
Yeah,
It's only gonna be freeing nodes. It's not gonna be getting new nodes.
exactly. Yeah,
But it only needs the node pool.
yeah,
Um, so now, what do we do here? So I think first thing we do is like copy. Well, the simplest way to do this is to get an extra node, and then use that as our scratch buffer and copy everything from the first node into that, then everything from the second node into the rest of that if it's not full already. Otherwise, well, we could have a fast path though for when the first node's already full and like the first n nodes are full.
yeah.
Um,
Oh, that's the other thing is that a lot of the time it is going to be pretty compact because we only modify it
yeah,
in
yeah.
certain, yeah,
But as soon as we get to the place where we find a gap, then we have to start mem copying everything after that point.
exactly, yeah.
But you're right, like the first n nodes. So I guess the first thing to do is say, yeah, var node equals 0. Oops. Then we're gonna say like while node or array counts node is less than or is equal to node. I'm just gonna skip over the full nodes first,
Okay,
if that sounds good to you.
yeah,
Skip over any leading already full nodes. So now we've got our node is equal to the first node that's not full. Now we want to, I think, acquire a new node from the node pool and copy.
We also just need to take into account the logical number of nodes that there actually are. Otherwise, we might be going out of bounds here.
Oh yeah, good point.
Yeah.
So while node is less than array.node count, and that stuff is true. I'll probably just put this on a new line. It gets more readable like that now.
Yeah. Cool.
Yeah, and I think I'm just gonna say yeah. Const buffer equals buffer's not maybe not be the best name, but I'm just gonna call it for now. NodePool that and acquire or get node, what we've been calling it. Then we're gonna copy into buffer from this node.
It also we have to also restrict that because we might already be at the end of all the nodes. All the nodes might be at 100% capacity with none further left.
Oh yeah, sure.
Yeah.
So if node equals, we could also like just put this inside the, well, no, I think that works.
Yeah.
We actually you like restructure this and use like an else and a break instead, but I think this is simpler like this.
Yeah.
The other option would be like to put this inside an if this break and then here else return.
Yeah, that's cool.
And then you don't duplicate this check.
Yeah. And then internally the break is if it's less than node capacity, then break.
Oh yes. Thank you.
Cool.
And then we have here, maybe just start to make sure we didn't screw this up. I'm not totally happy with this though, to be honest. It feels more convoluted than it was before. The control flow is like all over the place. Like,
Yeah.
I'm going back if you're happy.
Yeah, sure. I'm with you. It's nice to just sketch it out and then you see both.
Yeah, for sure. This just seems simpler. It's more intuitive. Yeah, there's no fanciness.
Yeah. The other thing is we are going to need a loop anyway to go over the tail. So maybe instead of having an early return here, we just put that in a loop. That solves that problem.
Maybe I want to start. Let's leave it here for now. Maybe we can do that eventually once we write the loop and see how that works out. I want to see how the loop is going to look like first before we commit to that.
Okay.
But not sure we can easily. We'll see.
Yeah. Isaac, could you explain the scratch buffer idea to me? I haven't got to that yet.
Sure. Let's go to the whiteboard because that sounds like a good idea.
Cool.
So I'm gonna use squares for buffers. Oh, I could even like, I forgot how to do. Is it control? Oh, nope. Never mind. I'll stop trying to use this properly. Okay, so we've got our buffers in our array.
Yeah.
Okay, and now we've got items. Say like this one's almost entirely full. This one's also almost entirely full. It looks bigger, but they're all the same size. Trust me. And so this one's also like, let's say they're like all 90% full essentially.
Okay.
Now, our goal is to like compact this stuff to make them all the way full. Not gonna worry about load factors right now. And so the idea with that is or my idea, or how I think it'll work in my head right now, is to use a scratch buffer for this. And so we like take all this red stuff and put it into the scratch buffer first of all. And then we've got a free buffer. And then kind of store that as our next scratch buffer, this first node. This one's now empty. And then we take the first bit of this node and put that into here too, at that end. And then we still don't have this buffer free though. And so then we copy the rest of this into the first buffer, which we've just freed up. We know that will fit because it's now less than a full node. And so now we've got the free buffer for the next round. Does that make sense?
Yeah.
So we always need like one free buffer to be able to copy stuff into. If you don't have the scratch buffer, then what happens is you try and copy stuff from the second buffer into the first buffer, right? Right like that at the beginning. But then you don't have a free buffer to move this stuff in. So you then have to do like a copy backwards inside the same buffer. Maybe that works too, though.
I actually think that's the same complexity because we end up copying the same amount, but we don't have to swap nodes and all of that as we go. I think it's the same.
That seems like it would be simpler, yeah. That makes sense. I don't know what I was thinking then.
No, it's cool. I'm glad you thought of something different like that. It's pretty cool.
Yeah, then we just copy backwards inside this node.
Yeah.
Then copy from the next node. You fill the rest of that node. Yeah, that should work out fine. It's a little bit less clear when we get to free nodes, though.
Yeah.
I guess whenever we copy out of a node and it becomes totally empty, we free it.
Yeah. Exactly. Yeah.
I think that's right.
Yeah. And then we don't.
Let's look at that case real quickly.
Yeah. And I think with this strategy, we don't have an exponential copying going on. So every piece of data will be copied at most once.
Yeah, except for the very first stuff in the first node. That's fine.
Yeah.
I mean, it's the same complexity as what I was proposing, but we don't use an extra buffer, which is great. It also seems a bit simpler.
Yeah.
And so if we only have like a little bit here, and this we can then just copy right into there, and then we just free this buffer because there's nothing else left in it.
Yeah.
And then the next one is started off. Yeah, so we just free whenever we empty a buffer completely, just by accident or whatever, then we free it.
Yeah. Cool. And then we're gonna go and update the absolute indexes and stuff right at the end. Then we just do that in a single pass. Again, the same bulk strategy.
That seems good, yeah.
Not trying to do that incrementally because that'll make it exponential then because we'll have to loop over again and again and again. Yeah.
Yeah, definitely. Cool. So we don't even need this buffer thing then.
Yeah, can we do just one quick back of the envelope calculation? So the size of our table info is like 64 bytes roughly.
64.
And we're looking at like 2 million. And then, so that's 128 megs. And we can do 6 gigabytes a second. So it'll be 128 megs over 6,000 megs.
Type that in 128
over 6,000.
6.
And then times 1,000. So we're looking at a 21 millisecond latency spike. Okay. That's if we copy everything. But if we set our compaction threshold, we don't have to set it to 100%.
Okay, and so what would that look like then? Like we skip nodes if they're above 90%?
Yeah.
They're at 90% or above, and then
Yeah.
well, the same. As soon as we find a node that doesn't meet that though, then we've got to compact all the following nodes.
Yeah.
If we do this naively.
But then we only compact them until we get to a node that is where the threshold is acceptable.
So compacting takes away from the next node though, so it's going to kind of snowball.
Yeah. So what if we've got, like, let's say we've got 4 nodes and the first 2 are at 50% capacity. Then once you compact them, it doesn't snowball onto the next nodes.
Right. But if we've compacted them to like 90% in the last round, they're not going to be at 50% capacity. Or it's very unlikely that we have 2 on 50% capacity.
Yeah.
Um,
Does it not work out that there's some multiple and then it breaks the cycle?
um, yeah, probably. It'd be 10 nodes then for 90% capacity, right? Or something like
Yeah.
that.
Yeah.
'Cause you need to, well, it depends on how full the node is that isn't totally full. Um, like if we have, or, let's redraw some of these, I guess. I could get rid of that funky one too while I'm at it.
Yeah.
Okay.
Because the nice thing is if we do have some concept of a load factor, it means that our compaction gets amortized. It's not always doing 100% work, you know?
Yeah.
Mm.
Okay. And so we're going to say that this one happens to be only like 80% full.
Yeah.
I should probably just use numbers for this, to be honest. 80. This one's then, and all the other ones are 90, let's say, to start with.
Okay.
Yeah. I don't like that I can't redo things in this editor. There's just
Yeah.
no way to redo things. It's kind of annoying.
Yeah.
Anyhow.
Do you want to do this in your text editor in Cocoon?
Yeah, I think that's probably better for this.
Yeah.
Okay, so we've got nodes at 80, and then everything else is at 90. We can just have even more of those if we want. I don't know. Do we need more of these?
Yeah, let's add a few.
I should probably do this. Okay, and then so after compaction, we'll get this 80 up to 90, which means we'll steal 10 from the next one. So that one will be 80. Now we're just going to
Okay.
steal 10 all the way down
Yeah.
if we only compact up to 90. Um,
Oh, okay. So then we want to actually compact up to 100.
but then we won't have all these 90s to start with. We'll have instead of 100s to start with. This is like the
So,
scenario where
yeah.
where you compacted once to where everything was 90 after the compaction,
Yeah.
and you subtract, then you took away 10 from this node. You removed 10 things from this node,
Yeah.
and now it's not full anymore. And now you've got to compact again. And so then you take away 10 from this to move to that one. Then you do the same thing here and
Yeah.
here. Keep on going all the way down.
Yeah. So it doesn't work. Yeah.
No, the 50% works well because you can delete nodes.
Yeah. Yeah. But because you see, there is one other option if we don't do this compaction idea, is if we do like individual removes and inserts, you can also set a threshold higher than half. You don't have to use half as your threshold. It's the same principle.
Okay, yeah.
And
And then that
maybe
makes it
that's
just more often to copy stuff, but you'll result in a more compact tree overall.
yeah, maybe that's the better way of achieving this goal of having a compact array.
It also seems better with the latency spikes because like
Yeah.
20 milliseconds isn't really that good.
No,
Um,
it's not 20, it's not great. Like it's sort of breaking our, yeah, two is already a bit too much. Like one is okay. Yeah,
yeah.
yeah.
Okay, so how's that work with a load factor of over 50% then? Um, so let's look at insert first maybe. Um, since we already have the code done for that.
Yeah.
Here we look at, or we decide to split. Well, when we split, how would we split nodes then? Like we'd have to,
I think
we'd end up with one node that's even less full then, right?
we would still keep it 50% when we split, but we would do it when we remove stuff. That's when we would set a higher threshold.
Okay, and so removal, what's our threshold right now? So currently removal works how this comment describes it. Find the node as in and delete it from the elements array, decrementing num elements. If this reduces the node to less than half full, then we remove elements from the next node to fill it back up above half. If this leaves the next node less than half full, then we remove all its remaining elements into the current node and bypass and delete it.
Yeah.
That doesn't work for anything other than half either. Because you can't delete the next node then if you have so that
Okay. Yeah.
I wonder if you can like if you look at the next two nodes, can you then get like 66%, or 2/3? This reduces the node to less than 2/3 full. Then we are going to look at the next node and take. Well, we're going to look at the next two nodes. We'll see how many elements we have got in total. And we know that the next two nodes can be, well, that doesn't, because they could both be full too already.
Yeah.
Yeah.
So are you thinking then our compact method, we we don't do that uh, anymore?
Maybe not. I think we should just keep it simple for now. I think
Yeah.
we're kind of doing optimization before we know there's a real problem here. Um,
Yeah.
we
I
can come
thought
back and
I
not,
thought I thought the
yeah,
compaction would be simple, like brute force, but it actually turns out
yeah.
not to be. If it was simple,
Turns
then
out not.
yeah.
Yeah. I think we can make things a bit more efficient with these insertion loops. I think we should come back and do that, but I think the simplest thing to do is just to implement the data structure as it is normally implemented and just do this half factor.
Yeah.
Just finish up remove element.
Cool.
So we just do this to do then.
Yeah, let's do that. We'll be back.
Um,
But I'm
cool.
glad, like at least we've explored it and we know.
Oh yeah, exploring things is always good. We always learn something. And become more confident in the design we went with, even if we don't change it.
Yeah.
Um, so yeah. So we need to check now. We've checked. This is our check if the node reduces the node to less than half full. Then we move elements from the next node to fill it back up above half.
Yeah.
Cool. So now we just need to go for the next node and steal its elements. Um,
Yeah.
but actually, we should check first if this leaves the next node less than half full.
Yeah.
So we first need to find the count of the next node.
Okay.
If there is no next node, then we don't do anything. That's another thing.
Yeah.
So
The, what we can do though is we can also use the neighbor to the left.
um, I want to not do that for now. I think that's just more complex.
Okay.
It doesn't. We don't need. That's an optimization. That doesn't help us uphold the guarantees we want from this API.
Yeah.
You're right. They would make things more compact, but there's other things we can do before that to make things faster, I think.
Yeah.
Which
Yeah.
is just basically doing this in batches. Um,
But I think what we found is that like we don't really have a batch insert method that works. We kind of have to make these do it for us. Because
yeah,
we have already explored the batch interface where you make the modifications and then you do the compaction one off across all of that. But that it it
I think
yeah,
batch
but
insert does work actually all right. It makes the code more complex for sure, but I think it would
yeah.
be faster in the
Uh,
average
I,
case.
okay, so you mean
It's
instead of
doable.
splitting a node, we just rather insert two nodes, or
Well, I think it would look something like this. So examine all the places where we've got a +1 here. This would all be like become plus sliced at length,
yeah,
um, essentially. And the split node of full criterion would have to be changed pretty significantly. Um, it'd have to be less than this would have to be array that counts plus the insert batch size is less than node capacity. Then we just return cursor.
yeah,
Otherwise, we have to do something more complex. And first, insert as many as fit in this node, and then insert the second half of the batch into the new node,
yeah,
um, essentially. Or actually, no, we'd have to first split the node is what we would do, and
yeah.
then insert the two halves into the two splits or something like that.
Okay,
It gets tricky, but it would save us copies over this loop.
yeah.
Um,
Okay, cool. I'm with you. So that's nice. That we can do later. Um, uh,
Yeah, and that's why I want it gets pretty tricky though, so I wanted to have the tests in place before we try to do that,
yeah,
just so we can get a quick feedback cycle on whether our code actually works or not.
yeah,
Like with this stuff, I'm fairly confident we can just get it right first
yeah,
try, because with only like one element at a time, it's not that bad. But for batches, it gets a lot trickier with the edge
yeah.
cases.
Okay,
Um,
cool.
so if a current node is the last one in the node, equals array.last.node return. Um, the last node allowed to be less than half full. We can reorganize this code in a minute if you like, but I wanted to just do that there for now. Um, so the count of next node is going to be. So what we're checking is if this is our criterion for removing the next node, and that's going to be if the two counts are less than node capacity together.
Yeah,
Um,
less than or equal
plus,
to.
yeah. Um, so kind of want to have a variable for node, just because we're repeating it so much.
Yeah,
Eventually, we'll have like destructuring or something, so we can just like say node comma relative index equals this.
yeah,
Um, but that's pretty far off because it's just sugar, so it's
yeah.
not a priority at all.
No. I was thinking if we do get into left and right stealing, then we could be calling it A, B, and C. So B is the middle node, the active node, and then A is
Yeah,
to the left, C is to the right.
that does sound like a good naming scheme if we get into that,
Mm,
which I think we may try to. I'm not sure yet. I
yeah.
definitely want tests in place before we do that kind of complexity, though.
Yeah. You know,
Um,
with the test, it's actually just going to be really easy. We can take from the standard lib a linked list implementation, and that's it. So we do fuzzing. So we choose a random location to insert at, random amount of elements, and whatever we do against the segmented array, we do against the linked list, and we just keep comparing them for equality.
hmm.
Or we
Why
don't
not just
use
use
it.
like an array list?
Array list also,
Only,
it doesn't really matter which one we use. We can,
yeah,
yeah,
makes sense.
yeah,
Cool. All right, so now we've determined that all of the elements fit inside the current or a single node. So now we're going to copy everything from the next node into this node and delete the next node. Yeah.
yeah.
Pointer, I should make variables for this. Count. And then here, like next count, I guess.
Yeah. Let's do like B count and C count, so then it's lining up and we can see.
Count B, count C.
I think if we do the count as a suffix is better because we're going to have maybe pointers for them as well. Or yeah. And then node is actually B and node plus one is C.
Okay, yeah, we can do that.
Then it makes the code like nice and blocky and you can just scan it and see, okay, it all lines up and it's
Oops.
then I don't know if you saw in EWA, like it worked quite well where we did that because it literally that going from source into target was like the mirror image.
I can't get rid of that node.
Yeah.
There's too many nodes.
Yeah.
All B. This should actually be C.
Oh, that's
I'm gonna mess this up
array.
too.
Array.count.
Yeah. How did I mess this up?
No problem.
I think I was just writing node counts the whole time.
I didn't even see.
I don't know why.
Uh,
So array.nodes here, so that's right at least.
yeah.
It's gonna be B, and then we can add in C later when we need it.
Yeah. And then we can call pointer also can be B pointer. So it's clear whenever we use
Sure.
pointer, we can see straight away that this is going into B.
Still some more of these. B. I think that's it for now. Oh, there's still more. Man, I really did just all these. Okay, those are B. This is now C though. Actually, these are even, man. C count. B count. Okay, and B pointer. Starting at B count. To the end.
Yeah.
Actually, this could be even more explicit. And
Nice.
then from C pointer, we're going to go from 0 C count.
That's cool.
And maybe a C pointer. See, this might need to be defined in a bit higher scope. Okay.
And there
And
we need to
then in this case, we're
pass
gonna,
C. We need where we go, where we assign C pointer, array nodes, and then C
yeah.
as the node. And do we have C defined, Isaac? Is it higher up?
No, we don't.
Okay,
I think we should
cool.
do it like this then.
Yeah.
C equals B plus 1. Put C
And we
pointer up
can
there.
hoist B count right to the top because we actually use it.
Yeah. Oh, yeah. Um,
But then we've got to just be careful because we do a decrement on B's count as well. So now
yeah.
we're using a different one.
Yeah.
It I
Let's
think
not do it like that.
it
Define it
yeah.
down here,
Okay.
right?
Okay, cool.
So we did this very rigorously in this order, so we had the symmetricality here
Yeah.
with the 2 plus ones and the 2 not plus ones instead of a plus 1 nothing and a minus 1 and nothing.
Yeah.
Just more clear that way.
Cool. Maybe oh, where we do our first mem copy, we must use B pointer as well.
Oh yeah.
And then we could like drop the B pointer definition to be just before the mem copy where we use it the first time. Or what do you think?
I
Or
kind of
we're
like having the
not?
constants.
Yeah,
This is all
together.
business logic here.
Okay, cool.
And then
Yeah,
we've got more logic. Then we've got another block of constants. Then we've got logic again.
yeah,
Um,
cool. Then I think we should move the B count just above C count. So B
oh
comes
yeah.
before. Unless you want to
We're gonna do
move.
this.
Uh, no, yeah, that's perfect like that. That's nice.
Okay. Then we're gonna do we're gonna then delete the C node and shift all the metadata as
Yeah,
well.
yeah,
Um, free node. We might need a different API here. We'll figure that out though eventually.
yeah,
We probably need to write the NodePool kind of soon to test
yep,
this actually.
yeah.
Um, whoops. What do we want to pass here? This is gonna be the pointer. This is gonna be a C pointer. So I think we might actually need to have like a little struct there that has a like a, or we could do like a little trick. We'll see.
Yeah.
There's ways to do this. Um,
I think in the end we should do for our actual pool, the methods should be acquire and release because we do that
yeah,
in
some
block free set, and those two also line up nicely there. Yeah,
yeah, and then the IOP stuff.
yeah, yeah,
Yeah, I'll just call this one release then.
yeah.
Why not? Now we need to shift all the metadata. So this is gonna do like mem copy. Well, I'm gonna copy it from up here actually. Split node. The reverse of all this stuff. This one.
Yeah.
We probably want to refactor this too, but we'll
Yeah.
can do that after we look through it.
I was just thinking that too.
Um,
It'll kind of be like shift metadata left, shift metadata right.
yeah. This isn't even right because this needs to take in C node instead of, this needs to be C, not B. This should all be say C, but I think we should just, I think we're going to put this in a new function right away, so I'm just going to change this stuff and put it in a new function.
Yeah.
Let's see if I can do this better. Actually, no, I want to like go one back, then grab that, then do that, and then delete that. Yeah, I've messed it up slightly. There we go. Oh no, I messed it up. Damn it. Alright, I'm gonna stop trying to be clever and just do it. Sometimes you gotta just stop trying to be clever. Next time I'll get it. Alright, now this needs to go in a new function. Shift left. This needs to take a node. Okay, and then we need to also shift the other things. Scrolled too far. These things.
Yeah.
It's also right there already. Yeah, I should not copy them. Or rather, I copied something else. Okay. Node count minus equals 1. Nodes. Should this do the freeing as well? Maybe it should. Just kind of like delete node instead of create node. This is insert empty node. This is just delete node at.
Yeah.
That we're right now writing. I think.
Or yeah, we could call it remove empty node at.
And then assert that the node's empty. Yeah, that sounds
exactly.
good.
Yeah.
Cool.
Nice, good catch on the name.
Cool. Node count's gotta be greater than 0. Node must be in range. Assert. Nodes node count equals 0.
Is actually array.counts for node equals 0.
I thought I just did the same thing.
Cool.
Oh, what have I done?
That's
Interesting.
it. That's it. Cool. Node.
And I often wonders if this assert's really necessary, because that just means we have to set the count before we call this function instead of just letting the function handle it.
Yeah, then maybe the function should do that.
Yeah.
Well, oh no. You see, then it isn't an empty node, so then we have to rename the function.
Yeah, but here where we call it here, this node.release can go in here too.
Okay.
This stuff also needs to come first. Let's fix this up real quick. So this needs to come before we overwrite the stuff with a memcopy.
Yeah.
This stuff doesn't need to get changed. Or actually, hold on. There's one thing that needs to happen first, which is the node.release. NodePool.release array.nodes node. Something like this. Probably a dot question mark there. And then all this stuff we don't even need to do. It just gets overridden at the end. What we can do is set the stuff past the end to undefined, which I think is, or just zero it. Whichever one you feel like.
Just zero it.
Yeah. Node count -1 can happen here at the end, yeah. It has to happen here at the end, in fact.
Yeah.
Interesting. Are you change this to a -1 or do we like mess it up above? I already changed it, I guess. Cool.
Yeah.
I don't remember doing that.
Yeah. Is it
This is
okay, so we have to release it because otherwise we've overwritten the memory when we do the mem copy of
yeah, exactly.
array.nodes. And it just seems then it seems like we want to try and update the node count when we release it as well, but we can't because we reference that.
We use it in here, yeah. I think
Yeah.
node count comes at the very end of the function after we've done these things too.
Okay.
This is wrong though, isn't it? This is gonna do. Yeah, I guess we can just do it first. Or we can say array dot last node instead. I think that's good.
Yeah.
Maybe it's not. I think that's too much abstraction for this function. It's like a low-level helper function.
Yeah, I think with all these functions, we don't want to use helpers so that we can see that we're getting the order right of how we depend on the data.
Yeah.
Yeah.
So I think we do just do this first and that's cleaner. As
Yeah.
you see that we have an off by 1 currently if we don't do this first.
Yeah.
Equals 0, and then index of the first element. What do we set this to? Do we set this to 0 or?
Yeah. Or we set it.
Undefined safer than 0 here. The
I
0
think,
is just going to be totally wrong.
yeah, 0 is wrong. We can set it to the, it can be the previous node plus the previous node's count or 0. That would be a better value because then you can use it. It's always correct. I think undefined would be good if we don't possibly have a value to put in there that's correct. But if we use the previous node to work this out, then it is correct. So that's then better.
So there's two things. Either there's if we have a previous node, if node count is greater than 0.
Yeah.
And then we're going to set this to the previous node. Otherwise, we're going to else. We're going to set this. Oh, it's R for brackets. Okay. Array.node count.
Equals 0.
Going to equal 0. Yeah. And in this case, it'll be same thing -1. So Yeah. Does that look all right? It's kind of messy, I feel like, but
I don't know if
not
we've got it.
really.
It's actually going to be equal to the absolute
Oh,
index of the
yeah.
previous node plus that node's
You have a helper
count.
for that. You
Yeah,
want to use the helper for that? We've got last absolute index that does this with
yeah.
the right -1. I think we should actually use the helper here.
Uh, yeah. I don't know because that one is relying on node count. So when it does the assertion and node count,
Oh,
we might move that up
yeah.
or down.
Actually, we can't use it because it'll fail the assertion. Yeah.
Yeah,
So plus array that counts -1.
yeah.
Um,
We can always clean it up nicely here.
well, we've now okay. No, that works. Okay, that's verbose.
Isaac, I don't know what, do we have any shadowing for, is there anything called absolute index? We have that in quite a few places. So we can't, that, that field, we can't
Nope.
just rename it to absolute index. I
No,
think
we can't because we use absolute index as a variable name quite
yeah,
often.
yeah. Okay,
I think we should make the field shorter though, you're right.
yeah. We can
Call it
call
first
it,
absolute index.
okay, or we can call it AIOFE.
I think first absolute index is
Well,
still
eh,
is this more
okay,
incremental improvement?
well, here's even another idea. We just call it indexes, and the comment makes it clear what it is.
Sure, yeah. Yeah. I like that more. Um, so yeah, let's do that. That's good. Yeah. We could even call it absolute indexes if we wanted to.
Yeah, I think it's okay because we don't. Okay, well, we do use
Yeah, Ingham
relative
matches.
index. Yeah.
We use short names for these ones too, and so
Mm.
I think this is good. I look at
Okay.
how much cleaner that will make our code.
Yeah.
Look, this thing no longer looks weird.
Yeah.
Make that.
Yeah. Nice.
um, oh, I'm still pressing the wrong key sometimes. I'll get better though. This one too. Let me just like kind of grep through for indexes and see anything that looks weird now. Here, that's like where we just were.
Yeah.
Why am I doing that? Okay. It's still kind of long. Kind of typo. It's 127 characters. You know, we could write this slightly differently if we use like an
Use
if
a.
expression.
Yeah. Exactly. It'll.
Doesn't look too bad now, maybe with this adjustment.
Yeah. Just before the equals sign, where we do the actual assignment, before the if expression, we're just missing a right square bracket. Yeah.
And we're missing something else. Semicolon there. There we go.
Okay.
Eh, it still isn't great.
It's not bad though. It, it's better. It's better. Like it's much better.
I prefer like blocks here though, like when you do this kind of thing.
Mm.
This is actually under 100 too. But if I do this, it might be over.
Yeah, okay.
Yeah, it's gonna be over then. Okay, I guess we can leave it like this. I'm not so super happy with it, but it's all right.
Yeah.
Um, I like how these line up now, though.
Yeah. Yeah, that's nice. It makes it easier for the eye, like to pass it, to just to read it, you know?
Just to see what you're doing. Yeah.
Yeah. And
This
and
this is still weird though. I can't parse this at all. Just like the imbalance between this and this is just so great.
mm,
Um, that's what I'm complaining about mostly, I think.
yeah,
Putting it all in one line doesn't help. You can't do that.
no.
Like this, honestly, I'd rather read this, but it's too long. Um,
Mm.
maybe I better just do or maybe we just need a variable for node count -1, and then I can do the other thing.
We can't. We have to do it within the branch because otherwise we get
Yeah,
underflow.
let's do it like this maybe. Um, go back to this kind of if. And here we're gonna have here const previous or just prev equals array.node count -1 break.
Let's call it previous, like in full.
Sure. Oh,
That's
okay,
nice.
that's looking better to me.
Mm.
I've still got something that's incorrect syntax though. Yeah, I need to close the block and add a semicolon. There we go. How's that?
Nice. Nice. Yeah, that's
That's
cool.
that's legible now, right?
Yeah.
Um,
Well done. That's very cool. I think that's perfect. Yeah.
yeah, I can't stand the if statements that don't have curlies and are wrapped across multiple lines. I just think they look horrible. Um,
I agree. No,
if they're on one line, it's okay, but if they're on multiple lines, then it's really bad. I feel like I
yeah.
need to get Zig Forward to just stop doing that. Just
Yeah.
forbid that.
Yeah. Yeah. It's because it's an if expression, then you can't use
Yeah,
the curlies. Uh,
exactly. Yeah, but I think you should. We just want. I just think I just want to forbid if expressions across multiple lines. I
mm,
think they. I just don't like them. I don't know.
yeah. 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 I think that's a good idea. You know.
Blocks, or they seem more readable, and
Mm.
yeah.
You should do that, and then like in our case where we've got a hard column limit, then it'll force us to do the right thing, use a block,
Yeah,
and that's it.
yeah, maybe. I'm not sure yet. I'm not sure if Angel will like that or not.
Yeah.
um,
Yeah. What?
I still think there might be space for like somehow like instead of just using BLK everywhere, we could somehow have a nicer way to do this.
Yeah.
Um,
Yeah.
99% of the labels I use are just BLK, so
Yeah.
there's no reason to have a better name.
Yeah. Yeah.
Um,
Exactly. You know what we could do here is we could say if array node count equals 0, break 0, and that buys us a bit of line space, and then we might
oh,
not need to use previous, and then the whole construction
oh.
becomes shorter.
So we'd lose some indentation, yeah. I might just do it. Um, so
I'm not sure though if it's a good idea, but
it's still 104.
okay.
Um,
I think the
kind of,
other
I think
other
it's
way
more,
is more readable and balanced, you know.
I agree. All right, let's leave it like that. Move on.
Yeah.
Next problem. Well, actually, are we done with this now? We've freed the pointer, and we've overwritten the pointer, the count, and the index with new stuff. We've decremented the node count, and we've shifted all of these one to the left. That seems to be everything.
We just have to change the assert to say the count must be 1. No, that one
That's
is
right. What
right.
do you?
It's the third assert there. Yeah,
Where that counts node equals 1.
yeah, because
Why?
we've changed the semantics of this API so that this function does the decrement of the. Oh no, it's only decrementing node count. Uh,
Exactly, yeah.
okay, I got confused earlier. I thought we were going to change that.
Yeah, though I think we may not want this assert actually, because all that means that we need to then decrement this before we call this. Like here, what we're doing is going to be um, array remove empty node at, oh man, okay. Remove empty node at node pool C. But before we call this, we have to actually then immediately just do
Yeah,
counts C equals 0. Otherwise, we'll fail the assert.
but I think that's
This
actually
feels
good.
kind of redundant.
It's okay because the it's worth it. The otherwise, if we accidentally call remove empty node on the wrong thing, it's just going to delete data. Now we're actually checking that it is empty, and
True,
we're
but we can also
saying
do this on the wrong thing.
yeah, but it's much less likely there because well,
It does make things like less flexible. I think a
yeah,
lot of this is just making the code less flexible, and so you can't. It's hard. There's more things that you can do that are wrong
yeah,
without getting either an insertion failure or compile error.
yeah,
Um,
exactly. It makes the in a way it makes it brittle, but it isn't actually brittle. What we're just doing is really enforcing the contract, so there's no gaps. The
yeah,
it's tight, like which it should be. Yeah, because like remove empty node, the most important thing for it to assert is to check that the node is empty. Uh,
right.
that's so
Makes
important.
sense.
Yeah, because we don't know like where we're being called from. So I don't know if
Yeah,
there's anything.
that's definitely that's a good point.
Yeah,
Is this branch done then? Now we've seen that the combination of our current node that we just removed something from and the next node fit inside the capacity, or all the data there will fit inside one node.
yeah,
And so then we copy stuff from the next node to the current node, um, and then add the count of the next node to the current node,
yeah,
set the count of the next node to 0, and remove the next node. That seems to be it.
yeah.
Cool. Then we can return, or maybe not. We can maybe get rid of this return in a minute. I'm not sure yet. We need to
Okay.
handle the other case now where um, I guess not all of the next node fits inside this node. Yeah. This B is less than node capacity. Now we just copy enough to bring up B over half. Or to half.
Yeah. I like the way that we're doing it. We're checking, and then um, not trying to fill it up and then go and actually delete the other one. Um, just do
Yeah.
two specific branches.
Yeah, I think it's cleaner this way.
Yeah.
Less error prone too. It's also, this seems very simple. Like you just check if it fits. If it fits, do it.
Yeah.
Then the next check is that we don't even check anything now. We just take away from the next node enough to fill up B, and then we're going to assert that the next node it stays over half, and then we're
Yeah.
good.
Yeah.
Um, so const to copy equals um, node capacity over 2 minus b count.
We should maybe now capture that as a const called half, and we use it in both places.
Node capacity over 2, sure, yeah.
Yeah.
Oops. Node capacity. Half minus b count.
Yeah.
This is the number of new elements we need to copy to b. Okay, and so we're going to do the same copy essentially, but not exactly the same. Yeah, I didn't feel. Sometimes I just fail to press the key.
Yeah.
C count dot dot, and then instead of C count, this is actually going to be to copy.
I think.
Okay, then we need to fix up C.
Can we? Oh, okay. We can't. We're going to use to copy one more time still, so we don't want to do it all in line 3 times.
Yeah. Let's finish the code, then we can refactor it and make it pretty.
Yeah.
Then we need to copy within C. So C pointer. This is now needs to be a copy backwards, maybe.
Yeah.
Well, does it?
No, it doesn't, because it's also going to the left. Like
Yeah, we're
did.
good here.
Yeah.
Yeah. It's funny because backwards is actually forward. When you're going to the right, it's forward, but copy, yeah.
Yeah.
The semantics of copies are all weird.
Yeah.
I would blame C for that, though, I think.
Yeah, I would love in the standard lib that we can have copy backwards exact and copy exact. Yeah.
Yeah, I've been thinking about that. And I think one good way to do this long term is to kind of build because the standard lib is still under a lot of flux right now, and it's not really the focus of development. The focus of development for Zig right now is the self-hosted compiler. After that comes the language spec and the focus on the build system and package manager. The standard lib is kind of the last thing to really get standardized. It's standard library is the second to last thing, then documentation, and then 1.0.
Yeah.
And so I was thinking just so we can iterate quickly and see what works for us, is to just kind of start our own util file, I guess, for Tiger Beetle, and put the stuff that we plan on upstreaming to the standard lib in this as a temporary solution. And just kind of try them out in our code base to see how they work for us.
Yeah.
And then when we propose them upstream, we can say, hey, we've been using this for a while, and we think it belongs in the standard library.
Yeah. I think that's great. Yeah.
I think we should do the same thing with div seal.
Exactly, and that's also nice because we're not upstreaming all the time, and we're giving it enough time to actually check in our code base. Because maybe we're going to upstream it, and then next week we learn something better. So.
Yeah. I think that's a kind of a good compromise. We'll have the code in our code base to iterate on, and test it out, and then once we've been using it for a year, and this is pretty solid. Everyone else should be using this too, and then we can upstream it.
Cool. And you know what? Then we can rename utils.zig. What should we rename it to?
Tiger lib. Tiger STD.
Yeah. I think that's cool. Or standard lib extensions or something, or extensions. Extensions.zig.
Something like that.
Yeah.
Cool.
Yeah.
Or I kind of want to call tiger.copy backwards though.
Yeah. Cool. Yeah, let's do that.
Or maybe I don't know. We can also something like that. Anyhow.
Yeah.
C pointer. This is the same. No, this it's the C pointer. This should be from 0.
Hey, Isaac, I've got it. We call it STB.
STB.
Yeah, standard Beetle. Instead of standard, as our alias, instead of STD, we call it STB. STB.dev.
Standard Beetle.
Yeah,
I like it.
Yeah.
Cool.
Shall we do that? Yeah.
Well, STB is already a thing though. There's some really nice header only libraries. STB. That's the only problem with this. These are some super popular single header only libraries for C stuff. Like there's one
Okay.
that just like does PNG parsing and one that does like text formatting and whatnot.
Okay.
So doesn't stand for standard Beetle. It's like I don't know what it stands for. Um,
Yeah.
it might not say.
Okay. So you think
Anyhow,
we can't use that
oh,
internally?
initials of his name. It's Scene T Barrett. This is
Okay.
like a super well-known thing. This has got like at least in low-level communities.
Yeah. Okay. So we don't shadow that.
Maybe we shouldn't use that.
Okay. Cool.
We just call it Beetle. Um,
Yeah. Yeah. Or like
it's our
otherwise just extensions as a
yeah ext.
ext is
Um,
cool. Yeah. That's shadowing the ext file system, but that's okay.
we don't care about ext file system.
Yeah.
ZFS is what we use here. Nothing else is allowed.
Yeah. 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 Exactly.
Or just raw block devices.
Raw block devices completely. Like, yeah. It's much more fun, easier, you know.
Much more fun. Oh
Yeah.
yeah.
It is
So we're copying.
actually it is so much easier actually, like for operations, everything. Yeah. Yeah.
Yeah, I believe you.
Yeah.
Um, so now this is a little bit tricky now because we want to copy um to using the new C count. Um, so I think the simplest way to do this is perhaps copy dot dot. That does it correctly. Oh, no, this is not right. So that does it correctly, but we don't get the full bounds checking.
Yeah.
Yep. No, this doesn't end properly yet. This would be C count. We don't have bounds checking here. This will be actually then, if we want to add it, it would be C count -2 copy. But I'm not sure if we want that or not. It's not really helping us.
Yeah. It does help us eventually if we start using um, ext dot copy exact, then we would want to we'd have to pass exact slices in.
Indeed. Okay, yeah,
Yeah. Yeah.
true.
Yeah.
Let's leave it there then. And then we're gonna do oh, you know what? We can actually just assign C count. Well, I feel like that'd be weird. We need to fix the C count and B count now. Um,
Yeah.
doing these two or not these two things. Just ooh, oops, I had two curses. I didn't realize it. B plus equals C count. It's not that anymore. It's 2 copy now, and this is going to be C minus equals 2 copy.
Okay. What can we call to copy? Like a one word? It's the stuff that moves across. Uh,
Diff or
yeah.
hmm, it's not perfect.
So it's half less B count, and that's going to be more than half. No, 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 it can't be more than half, obviously. Uh, so B count is less than half, so that's good. Half minus B count. It'll be smaller than a half. That's a nice assertion also. But I think we need to do that on B, right? Not on C.
I think we can do that in C as well.
Okay.
Um, at least we should be able to,
Okay.
if I understand things correctly, because that means that B count plus C count was rate was strictly greater than node capacity.
Okay.
And so that means that if you take away, yeah, it means that this means that two things are true. B count is less than half, and B count plus C count is strictly greater than node capacity.
Yeah.
So that means that C count plus 2copy is strictly is greater than half, and C count minus 2copy is also still greater than or equal to node capacity. I'm pretty sure.
Yeah. Yeah.
Uh,
Can we just plug in some small numbers just to double check? Like, say node capacity is 10 elements. B count
all right.
is less than 5, so B count is 4. 4
C count is then
plus 10. Let's say C count is 10, so it is at node
right.
capacity.
Yeah.
So B count is 4, C count is 10. So we'll have 5 minus 4 is 1. We're going to move 1 out of 10. Okay, cool, that's correct. And we can
Interesting
then,
would be the other side, where C count is 7. That'd be the closest you'd get.
okay,
And so then you'd move 1 over. You still have 6, which is more than half.
yeah,
Or actually, this can be strictly greater than half, actually. Yeah,
yeah,
because
it has to be,
if
yeah,
because on the boundary, if it's equal to half, then you could have hit this path
yeah,
and gotten rid of it and had a completely full node.
yeah, cool. And then shall we do the assert on B as well, that it's greater than or equal to half? Well, actually, we
Um,
expect it to be equal to half now.
yeah,
Exactly. Cool.
cool. Have you thought of any better name for 2copy yet? I haven't been able to. I also need to
No.
update 2 more things here, namely
Okay.
the oh, just one more thing. The what's it called? The indexes for C.
Hmm. And over there, we just, instead of X, we've plugged X in as the indexes, which should be C. I actually think
Oh, and everything after that as well.
it's
Um,
yeah, I think it's a plus
oh,
equals there, actually, because we've taken away from C,
oh,
so we've extended the previous one.
and it's not everything after it either. It's just
It,
this single one because,
exactly,
yeah.
yeah. Yeah.
But actually, we are removing something, so we actually do need to update the things after this, right?
Yeah.
Yeah. Oh, we've already done that here, though. I see. Cool.
Nice.
We've already actually updated them once for the thing we got removed, and now we're just rebalancing stuff.
Yeah.
Cool.
Maybe, I don't know what you think. Like, we're probably only going to call remove empty node at, we're only ever going to call it from this function, not from anywhere else.
Yes.
Maybe we want to actually see all the logic in line so that we can see that we are also going to affect all the other stuff. But then again, we're going to run out of indentation. So maybe it's good how we've got
Yeah.
it. Uh,
I think we should just leave it like this and get rid of the return too, because we don't actually need it with this
yeah.
else.
Yeah.
I think this is good like it is now.
Okay.
Um, yeah,
If,
cool.
yeah. I was just wondering if we could check how we update the metadata in remove empty node and compare it with how we update it elsewhere in other branches. Just check that we're doing the same amount of things.
Node counts, nodes, counts, indexes.
Okay, and that's the last node. which is now
Yeah,
everything has
we've
been
overwritten
shifted.
the one that the node we removed with this. We've
Yeah,
kind of just overwritten that node completely.
yeah.
And here we don't need to update node count because we haven't deleted any node or added any node. We
Okay,
just need to update the counts for the two nodes and then the indexes for the next node, or for the
okay,
second node.
cool. I'm kind of actually happy with this overall, that we've got nice incremental operations in segmented array, and it's bounded.
Yeah, it does make it much easier, or it makes me a lot more confident in our static allocation that we're not doing anything weird.
Yeah,
Um,
yep,
it's very predictable.
yeah,
This can only do. Seems like the worst case will also be much less bad,
yeah,
or the worst case is much better known.
yeah. The only thing where we've got some bad exponential behavior is if we're removing a few elements, we're going to cycle through the absolute indexes again and again and again.
Right, and so I think we can have an optimization for that, but I think it's tricky.
Yeah,
Um, that's pretty much what my conclusion was earlier.
yeah.
Um,
Because it means we can't use cursor for absolute index inside remove element.
yeah, I think you kind of break it up into two stages. Well, I think the trickiness comes from the fact that the slice of elements you want to remove could be split across two nodes, and so you've got to do the removal across multiple nodes at once now.
Yeah,
So I think you then in that case split into two removals, and then well you do like both the removals, then you clean up afterwards, but it gets tricky.
yeah,
Excuse me.
yeah.
Um, I think we just want to get tests running and then come back to that.
Okay. I thought I agree with you on tests. What I thought is remove elements we could do, like we could make remove element totally private, and in remove element we don't actually update the indexes at all. We just go and do that right at the end, once over.
Oh, you mean this stuff?
That bit, yeah.
Yeah, we could do that too. I think it's the are more that's not as expensive as the copies though. I'm more worried about
Yeah.
the copies that are going to be we're going to be doing a
Okay.
copy for every time we remove an element.
Okay, yeah.
And we did actually put this in reverse order though, to slightly alleviate that.
Oh, of course. So that is actually fine. That's not an issue.
Or it's not as
Well,
bad.
it is still though, because as we go left, we're going to go more and more and more. We're going
Yeah,
to
it's just
keep
not
going.
as bad as it would have been otherwise.
Yeah.
Um,
Okay.
it's definitely be made more efficient by doing them all at once in like two groups if it's split across a node boundary. But that code's a lot trickier.
Yeah. You mean doing inserts and removes in one go?
No, I'm talking about splitting. If we get a batch of removes like that we do here, an absolute index and a count,
Yeah.
then instead of doing remove element one by one, we remove as many elements as we can at once, and that is not too bad, except for the fact that if your group of indexes you want to remove is split across a node boundary, you then need to deal with two nodes at once during this part of the logic.
Okay.
And then um, maybe there's a good abstraction we can use there to remove from only one node, but it gets a good bit trickier. But it's definitely possible to do that, and it would
Yeah.
be a lot more efficient for
Yeah.
batch removes.
Yeah. Okay. Maybe what we must do then now is like get our NodePool up, get tests, and then see if we can give it a shot to actually do our batch remove. Because maybe we'll
Yeah, I think
find
that's
maybe we'll find our batch remove actually becomes simpler, like compared to what we've got for an individual one. If maybe
I
we can
don't
just
think so.
find a nice design. Uh,
I
it's
think it'll be harder than a single remove for sure, but it won't be that bad. It'll be some pretty similar code. Um, Yeah, the same thing for insertions. Like you can do the same thing to optimize these
Yeah.
and just do like deal with the whole batch at once.
Yeah.
And then you need to deal with it being split across node boundaries,
Yeah.
and then kind of break it up into 2 per node insertions.
Okay. Because if we spend another day and we can get that done, then it's worth it because then we don't have to come back to it ever. Like it's just it can't it's pretty much done, you know.
Yeah, that makes sense.
Yeah.
We definitely want tests, and well, we need the node pool next, I think, and then tests, and then we can start trying that.
Yeah.
What are we doing in this? We've got remove implemented.
Yep.
We've got that
Got that
too.
done.
So we're on to 3. Look at that. We're
Yeah.
actually doing our to-dos.
Awesome. Awesome. High five. Yeah. Because
Um,
what I really
you want to take
like a quick break. Yeah. Yeah.
yeah, and then come back and do the tests. But
Yeah.
go ahead.
Yeah. What I was thinking is what I really like is that the design stuff is so solid and almost everything we've done, it's scalable. There's no leaky abstractions. There's no debt anyway. It's pretty much as optimal. Like our compaction that we did, we went for the jugular and just made it. It
Yep.
can't really get better, you know. I don't think unless we
Yeah.
learn something down the line and then it makes sense, then we make it better. But it's not like we
Yeah.
know
Well,
we've
we haven't
left a
done
whole lot
some
of
parts yet, but yeah.
yeah
I mean, there's always the case that we can learn more in the future, but for our
yeah
current knowledge, it does seem quite optimal.
yeah
I think the trick is just going to be selecting the right tables to compact.
exactly yeah
Might be a bit
yeah
tricky.
yeah.
We'll see.
So if we can, if we're not going to take too much longer to close the loop, if we do another day and we get segmented array like totally locked down, solid, it's really nice because later on, if we try to do it, it will take us 3 days, you know, to get back into the space. And
Yeah.
um, yeah,
Cool.
yeah, catch you
So
like
shall we 5 minutes?
yeah, yeah,
Cool.
awesome, awesome,
See you back then.
awesome. Hey Isaac, we back on?
Hey,
Cool.
cool. So, shall we do the node pool now, or just get into the unit tests? I guess we kind of need to do the node pool first, don't we?
Yeah,
Um,
yeah. I was thinking of how we could do the test, but we need to do the node pool. But can I just run it by you quick? What I was thinking.
sure.
So I thought we just have a simple reference implementation, which gives the same like query methods and insert elements, remove elements, same API, and internally we just shim out to array list or something. And then what we do is we do a fuzz test and we do like some amount of loops. And each loop we make a decision and say, okay, how many elements do we want to remove from? Sometimes we'll remove zero, sometimes we'll remove everything that's there, and other times we'll remove, somewhere in between. So those are the three remove options. Then we'll remove, and then we'll also then as soon as we finish removing, we'll then run a routine, which for every single index calls like, cursor for absolute index on both implementations, checks that they give exactly the same for all, that kind of thing. And then we do the same thing, insert, like, are we going to insert zero elements or insert like a huge amount of elements or somewhere in between? And then after we've inserted again, we do all our read methods. And sometimes in the loop, we swap the two around.
Cool. That makes sense.
Or
Yeah.
yeah, or we even do it that we each time around the loop we decide, are we going to do an insert or a remove, because that way what will end up happening is that you'll sometimes do lots of inserts or removes or
Yeah,
interleaved
that
or
sounds good.
yeah, anyway. So
Cool.
node pool.
That sounds great. Yeah.
Yeah,
Nice and simple too.
yeah, cool.
Yeah. Should we do the node pool? Um, yeah. So it's basically going to be source else. Um, so how big are our nodes? Node capacity, node size, which is generic. So
Yeah,
we should probably make this like use a node size. What are we passing in here? Level manifest, node size. Where's this come from? Nowhere. It just is a constant. All right.
cool.
So then config maybe?
There we
Yeah,
go.
it is. Cool. To also manifest node size. So we don't want to use that for testing this. We should probably just make it generic over the node size.
Yeah,
I've got to add it to my Git index so that it appears in my search results here. Because I only use like the output of Git ls files in that fuzzy menu thing. Um, Anyhow, let's make this generic for the node size. Comp time, node size, type, turn, require. So we'll turn a node, I guess. Well, I think we might need some like a small amount of metadata around this node. Like we need to store the node, but we also need to like be able to keep track of nodes in this here with some kind of data structure. And so um
like
I'm gonna call this node for now.
intrusive memory.
Yeah. Or maybe we don't require that. Actually, no, we don't need that actually. We can just have we can use field parent pointer to yeah. Or maybe hmm. So it'd be nice if we could just hand out pointers, and then the code outside this would not have to worry about how we kept track of the pointers, right?
Yeah, yeah,
Um,
exactly. That would be better. Like message bus, we've got message has got its own like intrusive memory.
yeah, but we also use that for FIFOs and whatnot in the replica
Yeah,
outside of the
yeah,
message pool,
yeah.
which
But I
is
think here we just want to return a piece of memory.
yeah. But then we still need to be able to keep track of the pieces of memory and like free the right one, or like when free is called, we need to be able to access some metadata about them. And
Yeah,
so um, one way I see to do that is to have a kind of node struct like this, where we have essentially a buffer field or a data field. There's an array of node size, and then we have just U8. Oh, where's 8? There, man. I've messed up my yeah.
yeah,
I definitely changed too much at once this time on my keyboard. Anyhow, next would just be an optional pointer to a node. And then here we would just return a pointer to a node size U8. We should probably like guarantee some kind of alignment for these nodes too.
yeah.
Um,
And then are you thinking we allocate a little bit of extra memory for these linked lists?
um, well, we don't. We just kind of allocate these nodes on the heap.
Yeah,
Um, and then you can go from essentially the pointer to this field, which is essentially this pointer here, and
yeah.
then get to the pointer to this struct. You can know where node is. Essentially, you just kind
Okay.
of stick this point. If you think about the data layout on the heap, it'll just be
Yeah,
like we've got a whole array here, and then there's a single pointer at the end of that array, which happens
yeah,
to be the linked list for our allocator. You also
yeah.
switch the order around here if you liked.
No, that's cool.
Um,
That'll add like 9 bytes of memory for the optional pointer, right? Or is
this is only 8. This normal 64-bit pointer.
okay.
Optionals are free for pointers because you just use the 0
Of
address.
course, zero. Okay. So it does cost like it's an extra 8 bytes times 2 million, or I think we do even more than 2 million.
We do 2 million nodes. I thought we did like 2 million tables.
2 million tables. Yeah. Oh, it's okay. Yeah, no,
We have
that's fine. Yeah.
or maybe we don't.
What?
You're right. We don't necessarily have to have this bookkeeping, but I think we do have to have this bookkeeping at some level because
Yeah. What I was thinking, like,
either we
this is
have
just
this or we
another.
have an array of pointers in this node pool. Um,
Oh, here's another option. We just allocate one big slab of memory with a single pointer and that has got all the nodes in it. And we keep track of the base pointer address. And as we get a node back, we can use that pointer to know where to put it, which one has been freed. We can then work out the index. We start getting a logical index into our big piece of memory. And then
okay,
the only thing we need is a free set, a bit set, just to track which nodes have been allocated.
it's like
And
the
that'll,
block reset. Yeah,
yeah, so instead of costing 8 bytes per node, it's down to 1 bit
yeah,
per node.
it's definitely more efficient.
Yeah.
Um,
And it's kind of simpler, like a lot less bookkeeping code, um, because maybe
it
it'll
could be. I
end.
think it'd be simpler this way, but you wouldn't even need a
Okay.
block reset. But this is it'd be just like the message pool essentially, where you just have two parallel linked lists
Yeah.
like
Yeah.
or just one linked list even of just free nodes. And acquire is
Yeah. Yeah.
just if the list is not empty, return the first thing in the list.
Yeah.
Um, and then release is just put the thing into the list. That's all the
Yeah.
bookkeeping you would need. But with the
Yeah.
free set, a little bit more complicated, but it also is more efficient memory wise. You're right.
Yeah. It does also mean you don't even have to update any linked list stuff or keep track of that. You just literally set a bit, unset a bit. Uh,
Yeah, it's the same thing, really.
And in a way, you do get a little bit of safety because if something is released twice, you can catch it. You
True,
can
yeah.
check.
Otherwise, you just
Yeah,
corrupt your linked list.
yeah,
That's definitely a good argument to make there. Um,
yeah,
Otherwise, you just kind of corrupt your linked list and you've messed up. Um,
yeah, yeah,
let's Node is not going to be this anymore. I think we also want to make it like aligned, so we don't have to align cast everywhere. We could like make it nodes aligned to like 8-byte boundaries or 16-byte boundaries or something like that.
yeah,
Um, um, I don't know. Is 16 overkill? It probably doesn't matter that much.
yeah.
Maybe 8 is fine. Actually, we do use 16. We do need 16 by alignment though, because we have checksums in our table infos.
Yeah,
Um,
yeah, yeah, we do.
so 16 it is. We also do like an aligned alloc essentially to allocate the node memory and then store 8. Should we just use a line of U128 here then instead of
Yeah,
16?
yeah, that's clearer what we're thinking then.
Avoid to, well, it's not even avoiding the need to. It would be like undefined behavior if we didn't do this.
Yeah,
Um, or
we
just,
could say
yeah.
a U128 is the biggest field permitted in a table info. Is the
Um,
biggest alignment
yeah,
required by a table info.
yeah. U120 is the
Maximum alignment.
maximum, yeah, has maximum alignment of all data we store in nodes.
Yeah. We should then cross-check this outside and bind the two together. That
Well, we'll actually get, if we don't, as long as we don't do a line cast, which we now won't have to because of this, we'll get a
mm,
compile error if we mess that up.
okay.
Um, that's what having alignment in the type system does for you.
Yeah.
Um,
Cool.
now let's just return
Yeah,
this node.
it's very nice. Yeah. And it's public function.
Sorry?
It'll be a public function
Oh yeah, and take a
and
node pool.
take a pool.
Or just not pub const. Node or just pool maybe.
Yeah, pool's cool.
Node, um, and then release is going to be this. We'll just panic if it doesn't
Yep.
um, succeed.
Yep. And then we'll have an init dinit.
Yeah, init and dnet can come in here too. This one can AR, I assume, because we'll pass in the
Yeah.
allocator here.
Yep.
So actually return
And
self.
Okay.
Um, void.
And then we'll have a buffer field and we'll have a bitset field.
And this can be what? I guess we could probably want bounds checking here. It's gonna be runtime
Yeah.
allocated. We'll have to compute the buffer size, I think, soon. I'm just gonna make this a pointer to the right line of array then.
Yeah.
And the bit set,
I think the size of the buffer will be runtime known.
really?
No, it will be comp time. Well, it will depend on the number of trees. It'll depend on it'll also depend on the storage allocation. And the storage allocation is only runtime known.
So let's just make
But
that a slice then.
yeah, although maybe we can see if we can tighten it. Maybe we can because we know tables max. I just can't remember.
It's not too hard to make it, to change that later if we want to.
Yeah.
Is this gonna be an ST dynamic bit set for now? Or do we have
Yeah.
like the roaring stuff? We don't have that merged yet, do we?
No, that's only it's EWA. It isn't roaring, and it's only the
Or
EWA
yeah,
compression.
sorry.
It's only the compression decompression like the codec. So we still have to use standard bitset.
Cool.
Yeah.
Oh yeah, that makes sense.
Yeah. So this will be dynamic bitset
Um,
unmanaged.
I'm just gonna go look at LSM tree. It's not here anymore. Block free set, yes. Call it free,
Yeah.
like we do there.
Yeah.
Um, what is ELS is complaining about something, but I don't know what it is. Everything looks fine to me. I'll just import the std.
Yeah.
Oh, it's parentheses.
Ah, there we go.
There we go.
Cool.
All right.
We could rename buffer to slab.
Sure. I don't have a strong preference there. You just wanted to line them up, didn't you? It's not really a slab allocator though, so that seems misleading to me. It's more like a
Okay.
pool and then a free. Pool is also 4 characters though.
Yeah.
Um, then we should probably call this something else though. Call this NodePool.
Yeah.
Or, I don't know. This could also just be
Buffers.
data. Buffer actually wasn't bad.
Yeah. Or we could call it nodes.
But it's not an array of nodes though, it's a slice of just raw data. You've got to kind of like
Yeah.
get the nodes out of it by doing some
Yeah.
tricky stuff.
Yeah. Then
Um,
just buffer. Buffer is good.
cool. All right. So our net and dnet we can probably steal from here as well. Whoops. It's not a block free set. It's going to be
Self.
NodePool.
Oh, it'll actually be self because it's generic over the node size, right?
Oh, yeah, you're right. Fit that or pool.free.dnet allocator. We need one more thing here. We also probably want to like change this around.
To hoist it. Yeah.
Buffer equals or alloc advanced, I think.
Yep.
It's not telling me.
Maybe it seems like it's changed.
That's why it's not telling me. Here we go. Alloc advanced. Type alignment n and then exact. Do8. Alignment is going to be eight. I've already forgotten what it was. I think it's n is next. Size and then exact.
And exact is
so
a
count should
enum
be
literal. We need to just add a full stop in front of exact. Yeah.
Count. This should be like a node, a count number of nodes, right?
Yeah.
This should be like a U32. Should be. We should call it node count. And then we'll have here node size times node count.
Yep. Just
That needs to be wrapped then. We'll
yeah.
For
Go.
And this needs to not be count, but instead node count. And then I think we're done.
Yeah.
Cool.
And we need to maybe set free so that it's got either all zeros or all ones.
It's already been set to all ones because we use a net full.
Ah, okay. Okay.
Yeah.
Okay.
We said ones indicate full.
Yeah. Yeah.
So yeah, we should be good there. Okay, I want to put this on one line and extract this thing.
Node count times node size.
Then you can put it like on one line like this.
Yeah, that's cool.
It reads a bit nicer, I feel like.
Yeah.
And then that's it. That's initialization. Dinit just needs one more allocator call.
To free the buffer. Nice.
These ones are gone. Okay. Wire. This is going to be, we're going to get the first free set. Let's look at block free set. We already did these, didn't we? Let's copy this. What does Kudu say? Ensure this unreachable is never reached. The leader must reject new requests when storage space is too low to fulfill them.
Yeah, that's when.
I think we might want to change that to be a panic. I'm not sure.
The reason is, so what we want to do is handle this higher up in the control plane, like so the VSR stuff, we will actually just stop accepting requests when the storage is full.
Okay,
That way
interesting.
we remain up for queries, for read queries.
Right. Yeah, that
Yeah.
sounds way better. So we don't just like crash when we fill up.
Yeah.
Yeah. Cool. So we should have the same to do here then.
Yeah.
Um,
We should
Except
actually
instead of
say
an
that
address, when
we should say the primary, because what I want to do in VSR is just rename wherever we say leader, just say primary, and where we say follower, say backup, so that we're just using full-on VSR terminology, you know?
cool. Sounds good to me. Okay, and find first set or else unreachable. That means we just get the first free bit, then we unset that bit in our address. See here we've decided not to use the 0 address for some reason. Which
Yeah,
we don't have that restriction here, so we don't need this +1.
exactly. Yeah.
So we may call this, instead of bit, call it like node or node index.
Yeah.
I'll just use node for now and see if we want to like refactor that name. And then this is also not yet true. We just need to then divide. I guess it's just return pool dot, or it's not this. It's we're gonna have to slice this buffer. We're gonna start at node times node size, and we're gonna go to node size. We're gonna go 0
Up
node
to node
size to
size.
get a compact node slice. And if this doesn't give me the alignment I want, I'll be kind of sad, but it probably won't because of stage 1. I should fix that at some
Yeah.
point. I think it might already be fixed in stage 2. I'm not sure.
Yeah.
Um,
And
so it
Isaac, I
doesn't
was
properly
wondering,
alignment through slice this properly.
yeah,
Um,
yeah, I remember. I was wondering here if we're now having a slice, can we still use the slice pointer to get into the big buffer? Does it not change things? Because the slice also includes the length.
Sorry, I'm not following. Um,
Is it fine to take the slice pointer into the pool.buffer? That's fine to do pointer
yeah.
arithmetic, because the slice type is also including the length. But I guess it's not going to store the length before the pointer in the slice. It's going to first store the slice pointer and then the slice length within the slice type.
It's not it's not well
Oh,
defined how the slice type is stored in memory. Um,
and the slice type is going to be stored on the stack anyway. It's not going to be part of
yeah,
our,
it's part of the
yeah,
struct here. Yeah,
yeah. Okay, cool.
cool.
I've got
So
to,
that does what we want
I've,
already. It seems.
yeah, nice. I've got to jump for a call in 9 minutes.
Cool. I've got to get off then too. So you want to
Yeah,
wrap this up now, or I guess release is almost done.
yeah. Shall we do release quickly? Then we can pick up tomorrow.
I think we can do it very quickly. I
Yeah.
hope at least. Um, so we just need to get rid of this -1 and just say, well, we need to do pointer arithmetic to find the right node, and then we need to assert that free is not set, and then free it.
Yeah.
Um, so we can call this like, we can keep that called node, and we'll have call this like node index. And so we just need to do const node index equals or pointer to int node minus pointer to int pool.buffer.pointer. That's going to give us the memory address, and we need to divide this by node size.
That's it. Yeah.
We can give exact this actually.
Exactly. Yeah. Just thinking that too.
Node size. Done.
Nice. Cool.
And we didn't mess up the sizes either because these are both in bytes. So you don't need to divide by the size because UA has got size 1.
Okay. Do we want to assert that here too, that they are the same like that? We can do a comp time assert right here because this is where we use it and do the pointer.
Sure. I think we well, it's a little bit tricky. You have to do st.meta.lm node. LM is giving you a type, equals st.meta.pool.buffer. That'll do it.
Okay.
This will give you the child type of a memory span type. So given this type, it'll give you U8.
Okay.
It's pretty nifty.
Yeah, that's nice. You know what we should do too is just an assertion that the node pointer is actually within bounds of our buffer.
Oh yeah, we should do that too.
Yeah.
Yeah. We can probably do that first. Assert. This also needs to be important to int. Node is greater than or equal to pointer to int pool.buffer.pointer. And then I'm gonna do another one for the other bound. Assert.
Pointer to int node plus node size is less than equal to pool.buffer.len.
Yeah, well, you need to also subtract there though. Int node is node plus node size is less than or equal to
pool.buffer. I think
yeah,
it's
but
just
you also need to add. It's also then it's the pointer to int pool.buffer.pointer plus pool.buffer.length.
Of course.
There we go.
Yeah, that's it. Nice.
Cool. I think we've got it now.
Yeah.
All the asserts.
Great. Okay. Well, awesome work, Isaac.
You've only got 5 minutes now, so I think it's time to call it. Tiger Beetle Sessions, Tuesday, 25th of January, session 10, signing off.
Cheers, everybody.